Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the blind Leetcode 75 problem list. Today I will be doing problem 19, which is called remove nth node from end of list. This is a problem that I would say is a little bit more advanced than other problems that we've done with linked lists so far in the channel. So definitely one that you might want to try if you're starting to feel a little bit confident about your skills. So let's get to it. And given the head of a linked list, remove the nth node from the end of the list and return its head. Example 1, we have 1, 2, 3, 4, 5, and then we return this list because n is equal to 2. So it's the penultimate node because n equals 1 here and n equals 2. So we just return that. In example 2, if we just have the head by itself and n is equal to 1, then the output is an empty 1. Okay. And if the head is this, n is equal to 1, then we just return 1. Alrighty. So if you want to try this problem by yourself, now would be the time to pause the video and just give it a try, because now I'm going to discuss how to solve this problem. Alright, so let's get to it. So the first thing that I'm going to say, right, is that in this kind of problem, since we want to remove an nth node from the end, we might want to use recursion, right? Because as we go through the recursion, we go all the way to the end, and then we just pop back up on the stack as we go. So we go all the way to the end, and then from the end to the top again on the recursion calls, right? So using that feature from recursion calls, maybe we can take advantage of that and keep track of what node we're on, right? So the main idea here, right, is we just make a recursive, we start here, we make a recursive call, and then we keep making recursive calls. And then whenever we encounter a null node, that's when the recursive call will end, right? So then maybe using that, we can keep track of how many nodes we visited so far as we pop back up. And whenever we reach a number that we have desired, or the one that we want to meet, then that's when we perform the operation of deleting the node. So let's think about some base cases. Some of the ones that come to my mind is this one, for example, right? If the head is just, if the linked list is just one node, or if it's empty, then we're going to return an empty list. So let's start with that, just to start simple. So if head is equal to none, or head down next is equal to none, then we return none. And that takes care of two very basic cases. Now, what is the operation how are we going to do this removal, right? So how about using a helper method that keeps track of how many nodes we've visited so far in the list, and whenever that number that we encounter is equal to n, then we simply perform the removal operation. How's that going to work? So let's try an example. So let's start with this one right here. So the idea, right, is that whenever you encounter a node that is null, so this 5 points towards none, when we're going to do calls, right? And with the helper method, whenever it returns none, then we will start returning a 0, because that means that we have visited 0 nodes if we start all the way at the end. This will be the first node starting at the end. This will be the second node, third node, and so on and so on. The main idea here is that so we can use the helper method, right? The helper method is going to return an integer, so we can set some sort of integer equal to the recursive call. And whenever that integer is equal to n, so let's start with, here the example is n is equal to 2, right? Whenever the recursion call is equal to n, we will perform the removal operation. So here, right, we keep calling the recursion call, and here none is equal to 0. Then the recursion call ends, and then we're back on 5 on the recursion stack. So here what we have to check is, okay, well, has the recursive call returned the number that's equal to n, in this case 2? No. If that is the case, then we simply will return however many nodes we have visited before, like further down in the recursion, right? Plus 1. So this will return 1 plus 0, which is 1. Then we go here. What's the next one? Here we have a 2. we start with the previous, the previous. So here, we are at 4, right? And the recursive call has returned a 1. So is the recursive call, like, has it returned the number that's equal to n? 2? No. So what are we going to do? We're simply going to return whatever the recursive call returned, which is 1 plus 1, 2. So that means that this is the 0th node from last, the first one from last, and the second one from last. And then we pop back up to the 3. Has the recursive call returned a number that's equal to n? Yes, 2. When that happens, what we are going to do is we are going to look at the current node, right? And at that point, all that we want to do is simply return the next element. So we're going to make the pointer that goes from 3 to 4, in this case, current.next, or whatever we call it in the recursive helper. We're going to set current.next equal to current.next.next. So we're setting the arrow that points towards the 4 to now point towards the element that goes after the 4, in this case 5. So now 3 would point towards a 5. So we would do something like current.next is equal to current.next.next. And at that point now, the 3 would point towards the 5, and the 4 will not be pointed by anything. So it is effectively removed from the linked list. And then we just pop back. And this will be keep popping back and popping back. And there's one more case that we need to handle, right? So this recursive helper will just return these numbers. And this approach will work except if n is equal to the number of nodes that we have. Because the recursive helper is going to handle every case except this last one that I mentioned, which is whenever n is equal to head. So what we have to do simply is just call the recursive helper, and if the recursive helper, in this case, it's obviously going to return n, where n is the number of nodes. So if the recursive helper returns n, then simply what we want to do is just return the element that goes after the head, right? So let's get to it. So let's see, we have a helper here. And sorry, at this point, whenever we, I guess I didn't clarify. Whenever we return the head, whenever we've removed the element, whenever that happens, we will simply return, I think it'll be more appropriate to just return 2. We just keep returning that. Sorry, no. Ignore what I said. We're simply going to check whether n is equal to whatever this returns. And if n is equal to 5, then we simply just return head.next. So let's start with it. So define helper. So this is the recursive helper that we're going to use. And here we're going to use the head, and then we're going to use n. Remember that this is going to be returning an integer. So what is the base case for this? So if we find a null node, which is this case right here, then we'll return a 0. If that is the case, then we will just pop back up on the recursion. Now simply what we need to do is we can just call the next number something like that. So next is equal to helper head.next, comma, n. So remember that this right here will be an integer. This returns an integer. Now what do we need to check? Well, we need to check whether, remember how in 3 we checked whether next, so in this case whatever the recursion returned, if next is equal to n. So at 3, right, next, whenever we pop back from the recursion, next will be equal to 2. If next is equal to n, so if 2 is equal to 2 in this case, which that is the case, then we perform this operation right here. So instead of current, it's going to be head whenever next is equal to n. And that performs the removal. And what do we do next? Well, simply we just return next plus 1 because we visited one node more than before. And that's about it. In fact, I would say well, we need to handle the case. I forgot to say, yeah, we need to handle the case where the n is equal to the head, which I explained before. So we can say something like helper head n, and then we simply return the head. So this will remove it, and I think we can handle it on the base case too, is if n, actually, give me a second. No, we cannot handle that case here, so we have to handle it here. So we can say something like num is equal to helper. So we run all the elements, right? So we run all the elements, and this will be returning the number of nodes in the list. And that number of nodes in the list will be num. So this will always equal n. Sorry, not n. I guess n is the wrong number here, but num will always equal the number of nodes in the list, whatever amount we want to call that. That's called x. Okay. So if num is equal to n, then that means that we have to return the element that's after the head, because if n is the number of elements in the list, right? So suppose that in this case there are 5. If n is 5, then we have to remove the 5th element starting from the tail. So if this is 1, 2, 3, 4, 5, the way to remove the head from the linked list will be simply returning this list right here, which starts at the 2nd element, which is the same as head.next in the original call of the method. So if num is equal to n, right, then we simply return head.next. And that'll be the other case that we handled. So now let's comment this. And yeah, this code should work. And yeah, I've tested this before. It gets to like 19, which beats like 90% of all submissions eventually. But as usual, like the runtimes are pretty inconsistent in Leetcode. But yeah, there you go. This is good enough. So yeah, let's discuss the runtime and the space complexity of this solution. So let's see, what's the runtime complexity of this solution? Well, obviously, right, we're going to visit every single node in the linked list. At least, well, not at least, we're going to visit every single node in the linked list once. So clearly, the runtime complexity of this problem is big O of n. And what is the spacetime complexity of this problem? Well, the spacetime complexity of this problem, since we're doing n recursion calls, and we count recursion calls as spacetime complexity used, then the spacetime complexity of this problem is going to be big O of n, because we're going to perform, where n is the number of nodes in the linked list. I guess here they're giving us an n, so it might be a bit confusing, but it's big O of n for both the runtime and the spacetime complexity, where n is the number of nodes in the linked list. And the reason why the spacetime complexity is big O of n is because we do every time n recursion calls. So we go all the way down to the list, and like I said before, we count recursion calls in the stack as space used. And yeah, that'll be this problem. I hope you enjoyed the video. Make sure to hit a like, which helps the channel a lot. And see you in the next one. Bye-bye.